Alright, so in this video we go over sections 6.4 and 6.5 area, in which we will find the area under the curve and between two curves by integration. So suppose we have this graph of a function f of x like this, and okay, let's label this as f of x, and we want to find the area under this curve in between the limits x equals a to x equals to b. So let's shade the area that we wanted, and so really just like the definition of the derivative from the beginning of the semester, which is to find the slope of the tangent line at a given point, well, in this case the integral will give us the area under the curve. So the integral evaluated from a to b, that is a definite integral. That's what's going to give us the area under the curve. All right. And well, so from the previous couple of videos, we already looked at how to evaluate integrals, how to evaluate definite integrals. And well, so typically these kind of problems are just going to give us a function for which we want to find the area under the curve and the limits of integration for within we want to find those limits. So for example, we want to find this area under the curve for f of x equals x squared plus 5 from x equals 0 to x equals 3. So just you don't have to sketch this all the time, but I'm going to do it this couple of times just to see what are we essentially doing, so for example, that's a parabola shifted up 5 units and we want the area from 0 to 3. All right, we want this area, and let's shade the region for which we want that area. Let's find the area under the curve by using integration. So in this case, what we will do is integrate the given function a from 0 to 3 of x squared plus 5, and integrating these two individually using the general power rule, all we do is x cubed over 3 plus 5x. Evaluated from 0 to 3, and well, all we do is upper limit minus lower limit, for which 3 cubed over 3 plus 5 times 3, and then minus, in this case, notice that if we plug in 0 here and here, those two terms are just going to zero out. So in this case, it's valid to just call this a big 0. Right? So no need to write all that calculation there. And that's going to give us the following value. So area A equals to 3 cubed, which is 27 over 3, plus 5 times 3, which is 15, which equals 9 plus 15, which adds up to 24. And in this case, units squared. Typically, we express these final answers as units squared. Again, this could be centimeters, meters, kilometers, depending on the physical application. And that's the value of this area under that curve right here. All right. So let's look at another example, the exponential function e to the 5x from 0 to 2. And let's sketch this function again. So the exponential function looks like this. And from 0 to 2, let's just roughly sketch it like this. 1, 2, and we want this area right here under the exponential. So let's integrate from 0 to 2 e to the 5x with respect to x. And well, the integral of the exponential function is always itself, e to the 5x, divided or times 1 over the coefficient of x in the exponent. You can do, of course, a mini u substitution, but it's not necessary here. This one is a very straightforward one. That's from 0 to 2, and that's a 1/5 e to the 5 times 2 minus e to the 5 times 0. Over here, e to the 5 times 0, that's going to be, well, number 1, that's a 1/5. E to the 10 minus e to the 0, but be careful here when we evaluate the e to the 0. That's going to give us a 1. And 1/5 times e to the 10th power, which is simply e to the 10th power. Let's leave it like this, minus 1. Typically, we'll leave this in exact form unless otherwise stated. Well, you might want to leave this into, in terms of decimals, 3 decimals, 4 decimals, depending on the specifications. And well, so these kind of problems are just going to be very straightforward. Again, you're going to be given a function and the limits of integration. For area between the two curves, so let's consider the case right here in which we have a function f of x and another function. Let me do a different shape instead. Now, like this. And that goes from x equals to a and x equals to b. But in this case, we want to calculate the area between two curves within the limits of integration. Okay, it looks like a 9. Let me make it look like an a. And we want this area in between. So in this case, what we consider is to find the area of the under the top function. So that the picture right here is basically the following. That's if we want this area, we want to find the area of the whole thing above and essentially subtract this empty space that is the area under the curve G. All right, so minus this area right here. That's going to give us this area right here. And all we do is, so the area under F minus the area under G, and this is where our formula to find the area on between two curves is coming from. The area of the top function minus the area under the bottom function. All right, and let's look at a couple of examples right here. So let's find the area under the curve, under the curves y equals x cubed and y equals x squared plus 1. So area, which is the integral from a to b of f of x minus g of x. We need to be careful when setting which one is our f of x and which one is our g of x. For example, in this case, the f of x is always the top function and the g of x is always the bottom function. So in this case, this is the top, which corresponds to the function y equals f of x and y equals x squared plus 1. Let me make some change of colors here to be a little bit more consistent. Okay, and over here, this would be the bottom function, which corresponds to y equals x cubed. And while in this case, we are given the limits of integration from -1 to +1, they could be given in the form of an interval notation or in terms of vertical equations of vertical lines like we did before on the previous examples right here. Notice how they are given in this format. So either way, they mean the same thing. So let's find the area under these curves. So the area between -1 and 1 for f of x, which is x squared plus 1 minus x cubed. In this case, that's the top one, and that's the bottom one with respect to x. So my advice is to always write this in descending order of powers. That is negative x cubed plus x squared plus 1 with respect to x, and let's just integrate. That's going to give us negative x to the fourth over 4 plus x cubed over 3 plus x. All right, and this gets evaluated from -1 to 1. So in this case, upper limit minus lower limit, so negative 1 to the fourth over 4 plus 1 cubed over 3 plus 1 minus the evaluation at the lower limit. In this case, that's going to be negative 1 to the fourth over 4 plus -1 cubed, and be careful with the signs here, plus -1. You want to highlight this, okay, highlight with green, just so you can see where am I actually plugging in and how. All right, so let's simplify this. For the first group of parentheses, that's going to give us a -1/4 plus 1/3 plus 1 minus -1/4, because negative to the 4th power is still, it becomes positive, but times the negative in the front, that remains 1/4. And then negative cube becomes a negative, so that's a -1/3. And then minus 1 plus a -1, that becomes a negative. A few cancellations here, by the way. Notice how this -1/4 cancels with plus -1/4. And then we can reduce more terms to, okay, let's look at the thirds. So we have this 1/3 right here, and then minus -1/3, that becomes a plus another third. That's going to add up to 2/3. And then over here, 1 minus -1, that's a 1 plus 1 essentially, which adds up to 2. And combining these two numbers, that's going to give us 8/3 units squared, because this is area. All right. Let's have a look at one more example, and that's another example in which you may not be given all the information. So this is one example in which you are only given the functions y equals x squared minus 1. That's one of the curves to integrate, and y equals 1 minus x. As opposed to the previous examples, they gave us the limits of integration. In this case, our job right here is to find those points of intersection. And of course, I mean, they're here in the picture. I brought you the points of intersection. However, first, what we're going to do is figure out those limits of integration. So, and just to check with the work that we are given in the picture here, to check the results rather. So what we do is set these two quantities equal to each other to find those points of intersection. That is x squared minus 1 equals 1 minus x. And well, in this case, what we're dealing with is to solve a polynomial equation, and those are solvable by factoring. So what we need to do then in this case is have all terms on one side. So let's cancel, and that's going to give us x squared plus x minus 2 equals to 0. So we need to solve that polynomial equation by factoring. So we need factors of -2 that add up to +1 in this case, plus 2, and -1, because 2 minus 1 is 1, and 2 times -1 is -2. By the zero product property, x equals to -2 and x equals to +1, which are actually those points of those values of x for the points of intersection. Yes, we just check them. Again, in some cases you are not going to be given those values. You have to figure them out by setting the equations equal to each other to find the points of intersection. All right, you may not even given a picture. Well, in this case, I'm providing with a picture just to have a more visual example and essentially see what we're doing. You know? So now that we have the limits of integration, let's find the area under the curve. Area equals the integral from a to b of f of x minus g of x, that is the top minus bottom. And let's figure out which one is which. Notice in this case, this one is top, the line is top, and the parabola is the bottom. So for this reason, we're going to set the integral as follows. The integral from -2 to 1, top minus bottom, that is 1 minus x squared minus 1. Before attempting any integration, what we're going to do is to clean up the parentheses, and combine like terms. So in this case, well, let's distribute the negative. And that's the integral from -2 to 1. So that's a 1 minus x squared. And negative times a negative is positive. That's a +1 dx. All right. So that's area equals to, let's combine like terms at the same time. Let's write everything in descending order of powers. That's a -x squared minus x plus 2 with respect x, which in this case is going to be the integral of, well, we no longer write it in the integral symbol. We now integrate -x cubed over 3 minus x squared over 2 plus 2x from -2 all the way to 1. So the remaining part of the problem is fundamental theorem calculus, evaluate at the upper limit minus evaluate at the lower limit. I may not have enough space here, so let me go down here. So area equals, so minus 1 cubed over 3 minus 1 squared over 2 plus 2 times 1 minus -2 cubed over 3 minus -2 squared over 2 plus 2 times -2. All right, again, let me highlight with different colors so you can see what am I substituting and where. Upper limit minus lower limit. And so that's going to be, well, let's clean up parentheses and powers. A equals, so that's -1/3 minus 1/2 plus 2 minus, on the one hand, that's going to give us, okay, be careful here because negative cubed is going to become negative, but times the negative in front of it, this one right here, that's going to turn into positive. So that's an 8/3 because 2 cubed is 8. And then negative squared, that becomes positive, but times the negative in the front, that's going to be, remain negative rather. And in this case, that's 2 squared, which is 4, divided by 2, that's a 2. And then plus 2 times -2, that's -4. All right. After cleaning up parentheses, that's going to give us, okay, so that's -1/3 minus 1/2 plus 2. And then over here, I'm going to distribute the negative. What it does essentially is change the sign of everything inside of the parentheses. And that's going to be -8/3 plus 2 plus 4. All right. And well, after combining all these numbers using a calculator, the area should be 9/2 units squared. So On the homework again, you may not be asked to write that units squared. All you might be asked is to input the numerical value of it. All right. So this is the end of this video. I think this is a good place to quit. I'll see you in the next one.